Okay, in this lesson, we're going to take a look at how limits relate to infinite sequences. Now, the sequences in series was something you would have covered in Math 20-1, probably as the last unit. So, first off, remember that a sequence is a set of numbers with a definite order. So, the order or the pattern that happens continuously changes by whatever amount, whatever the pattern is, the pattern has to stay consistent all the way through, going from term 1 to whatever the last term is in that sequence. We can also see that in this case, it is an infinite sequence because of this ellipses at the end that says it's going to keep going on and on and on. Now, if we look at the sequences shown for 1, 2, 3, and 4, then we can use a pattern to state the limit or state that the limit doesn't exist, remembering that the limit is if it's approaching closer and closer and closer to a set number. So if I look at the first pattern, I have 1/2, 1/4, 1/8, 1/16, and obviously it's just going to keep going on to 1/32, 1/64, 1/128, going on and on and on forever. And because the fraction is getting smaller and smaller and smaller and smaller and smaller, it's getting closer and closer to 0. When I look at example 2, I have 3, 6, 9, 12, and then if the pattern kept going, I'd have 15 and 18 and so on and so forth, where I can see that the number just keeps increasing by 3 every single time. So it's not getting closer to a set value, which means that the limit in this case does not exist. When you look at example 3 can be a little bit trickier because I have 2, 1, 7/4, 1, 3/2, 1, 5/4, 1, so on and so forth. And really, we know that 2 is the same as 8/4, and 3/2 is the same as 6/4. So I am just alternating between 1 and numbers that are decreasing by 1/4. 8/4, 7/4, 6/4, 5/4, 4/4, 3/4, 2/4, so on and so forth. And because this is oscillating back and forth between 1 and a descending pattern, then in this case, the limit does not exist. In the last case, if the sequence is literally just that every term is 10, then obviously it is always approaching 10. Now, if we're given the formula to solve what every term value is in a sequence, like in this case, Tn is equal to n over n plus 1, then that means that term 1 is just going to equal 1 over 1 plus 1, which is just 1 over 2. Term 2 is going to replace n with 2, so I'm going to get 2 over 2 plus 1, which is just 2 over 3. Term 3 is going to be 3 over 3 plus 1, or 3 over 4. Term 4 is going to be 4 over 4 plus 1, or 4 over 5. Term 5 is going to equal 5 over 5 plus, 5 plus 1, which is going to give me 5 over 6. So we can already see the pattern. The numerator and denominator are always going to be one number apart, which means that if I went on to term 100, it's going to be 100 over 101. If I went to term 10,000, it's going to be 10,000 over 10,000 and 1. And as I divide these numbers, it's getting closer and closer and closer to 1, which means that the limit as n approaches infinity of n over n plus 1 is going to give me 1. So in general, the limit as n approaches infinity of t of n is just going to equal the limit. If the terms tn are as close as we like to L for the large values of n. So if I'm putting that into practice, like example 2 here, I'm going to say the limit as n approaches infinity of 1 over n would be the same as 1 over a infinity. Well, we can't plug infinity to our calculator, so it's just going to be 1 over a very large number. Now, as the number gets bigger, what's actually happening? Well, if I had term 1, it would just be 1 over 1, or 1. If I had term 2, it would be 1 over 2, or 0.5. If I had term 10, it's going to be 1 over 10, or 0.1. And if I had term 100, it's going to be 1 over 100, or 0.01. Which means that as the number gets bigger and bigger and bigger, then the decimal is getting smaller and smaller and smaller. So if I have 1 over an extremely large number, that's going to approach 0. So as n increases, Tn is getting closer and closer to 0, which means that the limit as n approaches infinity of 1 over n, we just call 0. In general, the limit as n approaches infinity of 1 over n to the power of r is going to equal 0 so long as my r value is greater than 1. If I have an r value that's less than 1, it's not going to hold true in the same way. At the same rate, the limit as n approaches infinity of r to the power of n is also going to equal 0 if the absolute value of r is less than 1, or we could say that if negative 1 is less than r, which is less than 1. If I use this for example 3, then if I'm asked, what is the limit as n approaches infinity of 1 over 3 to the power of n, then that's going to be 1 to the power of anything is just 1, and then 3 to the power of n because I'm going to apply that exponent to the numerator and denominator of the brackets. That's going to be 1 over 3 times a very large number. And if I keep putting 3 to a bigger and bigger and bigger exponent, then that is going to give me a bigger and bigger and bigger value. So I know that that would also be 1 over a very large number. And as we've already seen, 1 over a very large number is just going to approach 0. Now, how does that apply to example 4, which is, as you can see, the same as our example 1? In example 1, we know that this is going to approach 1, as we've already seen, so the limit should be 1. But how are we going to algebraically show this? Well, if I said that the limit as n approaches infinity of n over n plus 1, then what I'm going to do is I'm going to divide the numerator and the denominator by the variable to its largest exponent, which in this case is just n. So I'm going to divide the numerator and denominator by n. And that's going to give me the limit as n approaches infinity of n over n divided by n over n plus 1 over n. Well, we know that n over n is just going to be 1. We're dividing that by n over n, which is 1, plus 1 over n. And we know that if we have 1 over n, and n is going to be approaching infinity, then 1 over infinity, or 1 over a very large number, as we've already seen, is just 0. Which means that this is the limit as n approaches infinity of 1 over 1 plus 0, which is just the same as 1 over 1 or 1. We have another indeterminate form. Infinity over infinity is also an indeterminate form, just like 0 over 0 is an indeterminate form. To simplify the form of infinity over infinity, divide the numerator and the denominator by the highest power of the variable. In the last case, the highest power of the variable was just n to the power of 1. Then we're going to evaluate each of the individual terms. So, if we're algebraically determining the limit of this, then I'm going to say that the limit as n approaches infinity of n squared over 4n squared minus 2n plus 1, I'm going to divide the numerator and the denominator by n squared. We can see that that is the highest power of n. Then I look at the individual terms. So I'm going to say that this is going to give me the limit as n approaches infinity of n squared over n squared divided by 4n squared over n squared minus 2n over n squared plus 1 over n squared. This is going to equal the limit as n approaches infinity. Once we simplify it, n squared over n squared is just 1. 4n squared over n squared is just 4. 2n over n squared is 2 over n, once I simplify it. And then I can't really simplify the 1 over n squared, so I just call that 1 over n squared. And when I take either 2 divided by a number approaching infinity, or 1 divided by a number approaching infinity squared, then this is going to be 2 over a very large number, 1 over a very large number, and those are going to tend towards 0. Which means that if I have 1 over 4 minus 0 plus 0, then I just have 1 over 4. And there's my limit. If I'm solving the terms, then I would say that if this is my formula, then T1 is going to be 1 squared over 4 times 1 squared minus 2 times 1 plus 1, which is going to give me 1 over 3. I could sub in 2 for n to get T2, and that's going to give me 4 over 13. I could sub in 3 for n to get term 3, and that's going to give me 9 over 31. And the sequence for this is just going to be 1 over 3, 4 over 13, 9 over 31, and it's an infinite sequence, so it's going to go on forever.